Okay, today we're talking about blockchains. A show of hands, how many people have heard of Bitcoin? Okay, how many people have heard of blockchain before this week? How many people know how blockchain works? Okay, hopefully that'll be changed by the end of today. I've given this lecture a few times now, and I've really sort of struggled to think of how exactly to explain blockchain within an hour. It is fairly difficult, but I'm going to try and simplify it as much as possible and get you to at least understand the basic ideas of what's happening. So when somebody talks about blockchain, you'll now have a sense of why it might be significant and what exactly they mean beyond just this sort of mystical word. So we're going to begin with some light cryptography. Cryptography is essential to the blockchain. If you want to understand how it works, we're going to have to learn a little bit of cryptography to start with. Now, cryptography is simply the study of encrypting messages so that unwanted audiences can't access them. Now, this is really important for the digital world, but it has a much longer history than that. So, for example, here, in the background is one of the machines used in World War II to try and encode messages. I think this was the Nazi one. So this is one of the things that code breakers during World War II were trying to crack the code of this. They were trying to break the cryptography of it in order to get access to these messages. Now, today we want to understand hash functions. And hash functions are going to be at the center of Bitcoin, a blockchain. We'll talk about them a fair amount today. They're a very simple thing, but they're sort of complicated in practice. But I'll try and get the simple idea across. So a hash function is simply an algorithm which performs a series of mathematical calculations on an input to transform it into an output of a fixed size. So for instance, on the left-hand side, I could put in my name. The hash function would perform some calculations on my name, and it would output something like what we see on the right-hand side. A series of symbols and numbers and strings that appears meaningless, but has nevertheless encoded my name using the hash function. So that's the basic idea of a hash function. You take an input, you perform some calculations on it, it produces an obscured, encrypted output. Now, good hash functions have particular qualities to them. In the first case, each input should only produce one output. So if I put my name into that hash function, it shouldn't produce 3, 4, or 5 different outputs. It should only produce one single output. Now, the reverse is also the case. So every input should have a unique output. So that output shouldn't match up to different inputs. If you put in different inputs, they shouldn't go towards the same output. Some other good characteristics. Inputs of different sizes should be turned into outputs of a fixed size. So if we put my name in, it'll output, say, a 10-string character. If we put one of your names in, it should also output a 10-string character. It should always be the same size, and this makes it more difficult to determine what that input was. So it's obscuring the nature of the input. Another key thing, the output should appear random. So oftentimes when you look at sort of the blockchain community and the Bitcoin community, you'll see random strings of things like these on the side. Those are the outputs of hash functions. And they appear entirely random, but they're actually not. Crucially, it should be impossible to transform an output back into its input. This is probably the most important characteristic of a hash function. If I give one to you, you shouldn't be able to transform it back into the input. You shouldn't be able to uncover that it was my name which was the input. Otherwise, it's rather poor cryptography. You haven't obscured anything if people can uncover what the input was. I should mention impossible is relative to the state of mathematics and computer science. So one of the interesting questions going on in cryptography right now is what happens if we get quantum computers and they completely outpace current cryptography standards. So it may be possible in, say, 10 years' time, if we get quantum computing, that a lot of the cryptography that we use right now is easily breakable. So what seems impossible with current computers might be entirely possible with the next generation of computers. So impossible is sort of a relative term here. Now, a little aside, it's not crucially important that you know this, but Bitcoin uses what is known as the secure hash algorithm 256-bit. So it was created by the NSA. Obviously, the NSA has a very strong interest in making sure that things can be encrypted and that code can't be broken. So the particular hash algorithm that Bitcoin uses is this one. Okay. How does Bitcoin work? Well, I should ask, are there any questions so far about hash functions? Okay. The general idea is pretty simple, I think. Now let's move on to how does Bitcoin work? Blockchain is a more general technology. Bitcoin is a particular version of that technology, but it's a nice way to sort of get a grasp on what exactly is going on. So we'll start with Bitcoin. I'll give a general definition here of a blockchain. So a blockchain is a typically public, virtually immutable, distributed digital database. So whenever somebody talks about a blockchain, you can replace the word blockchain with this, and you can get a better sense of exactly what is meant in the context. And you can also understand when people are talking complete nonsense. So blockchain is supposed to solve, for instance, the Irish border problem for Brexit. That's absolute nonsense. The people saying that, oftentimes MPs, don't know what they're talking about. So it's a database. It's fundamentally a distributed database when we talk about the blockchain. It could be a digital record of events, so things like currency that's being moved around, goods that are being moved around, events in people's lives, health records, financial records. It's a database of these sorts of things. On a very basic sense, we might think about the blockchain as a spreadsheet which exists on a bunch of different computers. Now that's not all it is, but as a sort of basic idea, that's the sort of core aspect. Now I say that it's typically public since anyone can view the database. So for instance, Bitcoin's database, Bitcoin's blockchain, we can all right now go online and view every transaction that's been made on the Bitcoin network. It is a public blockchain. Now that's not always the case because currently companies are starting to use blockchains and they're making them private. So for instance, Walmart wants to use blockchain for its supply chain network. We can't all view that supply chain network. So they have a private blockchain rather than a public one. But most blockchains are public. It's virtually immutable in that it is difficult to change the blockchain. So this is one of the core things. When a transaction has been put onto the blockchain, it becomes very difficult, for reasons we'll get into, it becomes very difficult to change it. Oftentimes, people will say that it's impossible to change it. That's not actually the case. And we'll look at one particular case in which these things can be changed. But for most purposes, the blockchain is immutable. And it's distributed in the sense that it fully exists on each computer. Now that's different from each computer having a part of the blockchain. Instead, what happens is the blockchain exists fully on each computer. So everybody has their own copy of that spreadsheet. The Bitcoin blockchain, for instance, I think last time I checked, it's about 160 gigabytes in size. So everybody who's part of the Bitcoin network has 160 gigabytes sitting on their computer. Okay. Now the basic idea of a blockchain Wait a second, where are we? Okay. So that's the basic idea of a blockchain. Now we get into Bitcoin. Bitcoin is a decentralized digital currency. And it turns out people have been trying to build this for decades now, since at least the 1970s, a digital currency that wasn't controlled by anyone. And it turns out it's incredibly hard to do that sort of thing. There's a number of problems involved, and it wasn't until 2008 that somebody or a group of people named Satoshi Nakamoto launched this paper which solved all the sort of core problems of a decentralized digital currency. Now, nobody knows who Satoshi Nakamoto is. It's an anonymous name. There's been a number of guesses about who it might be. Curiously enough, people have done sort of linguistic analysis of this person's writings, and there's suggestions that they could be British. So maybe Satoshi Nakamoto is wandering around Kings, you never know. Yeah, so it's a really curious thing. You know, how do you maintain mystery in an age when none of us have any privacy, I think is quite an interesting question. So 2008, he comes out with a paper. They come out with a paper. Interestingly enough, 2008 is also the year of the financial crisis. And embedded in the very first part of the Bitcoin's blockchain is a reference to this headline. Chancellor on the brink of second bailout of banks. Now, this is often interpreted to mean that Bitcoin was designed to be an alternative to the existing monetary system of the globe. So 2008, the entire financial system is falling apart. There's massive efforts by central banks to sort of save the global economy, and Satoshi Nakamoto releases his paper to say, this is a better way of doing all of this. A decentralized digital currency is better than a centralized central bank currency. So that's sort of the political context for Bitcoin. But it turns out that making this digital currency is very, very difficult. So it's not just like an in-game currency or an in-app currency. An in-game currency is something which is controlled by the game designer. It's centralized, it's controlled. A decentralized digital currency isn't controlled by anyone, and this introduces some new problems. Now, the basic element of a digital currency, when we talk about something like Bitcoin, is simply that it is an entry in a database. So there's no physical object, there's no physical coin, it's just an entry in a database that gets moved around when people make transactions. So when I give Bitcoin to somebody, my database has that Bitcoin knocked off, somebody else's database has their Bitcoin topped up. So it's all entirely digital. Now the problem for digital currencies is who holds the ledger and who maintains it. Now typically when we work with sort of digital currencies today, when we transact digitally, there is a trusted third party involved. So it might be a bank like NatWest, or it might be a platform like PayPal, but there's some sort of third party which is overseeing all of the transactions. So this, we might think about these as sort of centralized digital currencies. Now this raises problems for the sort of Bitcoin community. They think that a third party is, it has a number of political problems. So, first of all, they see a third party as an imposition on privacy and security. So those third parties, the banks, PayPal, whatever the case may be, they can see all of your transactions. They can see what you're buying, what you're paying for, where the money is coming from, where it's going to. And the community around Bitcoin sees this as a really problematic aspect of existing currencies. The third party also controls who the transactions can go to. Now, in most cases, and for most people, this isn't really an issue, but I'll give you one example. Back in, I forget when exactly it was about 10 years ago, when WikiLeaks leaked a bunch of stuff about the American military, And what happened was the American governments put pressure on the third parties to block any money going towards WikiLeaks. So it no longer became possible to send money to WikiLeaks. You may agree with their political program and you may want to support them by sending money, but the third parties stopped that sort of action. So that's a potential problem with a third party as well. Now lastly, a third party is also a potential single point of failure. And this sort of goes back to the 2008 crisis. So 2008 crisis, banks start collapsing. And suddenly moving money around becomes incredibly difficult. And there's a potential there for the entire financial system to collapse as a result. So our reliance on these third parties puts us in a situation where we might lose the capacity to exchange currency. So that's another problem with third parties. There's a problem, though, if you get rid of third parties, which is the double spend problem. And this is one of the core issues that people for decades tried to figure out. How do you solve this for a decentralized digital currency? If you want a digital currency without a third party in the middle, you run into the double spend problem. So how do you prevent people from spending the same currency over and over again? So let me give an example. I send Bitcoin to somebody, and it gets changed in the transaction, and it shows up on their ledger, on their spreadsheet. But then I say, actually, I didn't send that money. I still have that money. Who is the authority which prevents that sort of thing happening? Who prevents me from spending that same money again and again and again? Normally, it would be a third party. PayPal would say, you've already spent this money. You can't spend it again. But without that third party to oversee it, how do you prevent people from doing that? So that was sort of one of the core issues that Bitcoin responded to, solving that sort of problem. Okay, so now we get to blockchain in Bitcoin. So I think a nice way to think about it is to compare it to a traditional ledger. So we've got a picture of a ledger here in the background. This, would be how accountants keep track of money that's coming in and out of a business. You mark down whenever there's any sort of transaction. Now we can compare the blockchain to that sort of thing. So in a traditional ledger, you would have a line and then a page and eventually a book. With a digital ledger, you have a transaction, a block, and then a chain, which is where the name blockchain comes from. So as I sort of talk about all of this, try and keep that in mind. A physical ledger is a good example of it. Are there any questions so far, by the way? Okay. Let's begin with step one then. So what happens when you make a transaction with Bitcoin? And I'm going to try and do this step by step and try and show you exactly how it all works together. So first of all, a transaction occurs. So one party transfers money to another person. So I might send, in this case, 5 Bitcoin to my wife. What happens is that transaction, as a message, gets put through a hash function. So this is the first place in which hash functions come in. That hash function then produces a hash value, which looks something like that. A random string of letters and numbers and symbols. Now, that hash value is then shared across the entire Bitcoin network. So it's sent out across the entire Bitcoin network. The Bitcoin network is every computer that is running the piece of software to be involved in the Bitcoin network. So right now, there's thousands and thousands, probably tens of thousands of computers who are involved in the Bitcoin network. So the hash is then shared across that entire network, and every single computer, every single node, checks that the transactions that particular transaction meets the rules. So these rules might be, has this person double spent? If they've double spent, then that transaction is canceled. It's not allowed by the rest of the network. Do they have enough money in their account? So if I'm spending 5 Bitcoin, but I've only got 2 Bitcoin in my account, obviously that breaks the rules of the Bitcoin protocol. So in that case, the transaction might be canceled. But if the transaction does meet all of the rules, it's then added to the local ledger. So the local ledger is the spreadsheet, the blockchain, that exists on that local computer. So it gets updated when it sees a new transaction that meets the rules. And this happens for every single computer on the network. Okay, so that's the first thing. Money is sent, it gets spread around the network, and then it gets sort of verified by each computer on the network. The next step is that a block is created. So a block is simply a sort of summary of the different transactions that have occurred in a set period of time. So what happens is you've got a number of transactions that happen in a certain period of time. Each of those transactions is a hash value, but then you can take those two hash values, run them through a hash function again to produce a new hash value. And you can continue doing this until you get one single hash value that summarizes all of the transactions that have occurred over the previous, say, 10 minutes. Does that sort of make sense? So you're constantly running this hash function as a sort of way to summarize the information that is contained within all these different transactions. A sort of technical note, if you end up reading into any of this stuff, this is what's known as a Merkle root. You don't really need to know that, but it's a technical term that pops up quite a bit in the literature. So all of the transactions are combined together through this mechanism into what's known as a block. Now, not every node on the network creates blocks. So performing those hash functions all this time can take a lot of computational energy. So not every node is doing that. Only a specific subset, known as the miners, are doing it. So when we talk about Bitcoin mining, this is what we're getting into. So they have to do all those hash functions, summarize all the transactions, produce a single hash value to summarize the block, but they also have to produce what's known as a proof of work. Now, in my experience, the proof of work is probably the most difficult part conceptually to understand about the blockchain. So if there's any questions at any point in time here, just raise your hand, let me know. So why is this proof of work thing necessary? It goes back to this question of the double spend problem. In a centralized system, you could simply trust that the transactions are recorded correctly. There would be somebody overseeing everything to make sure that the transactions were occurring properly and that no sort of funny business or any fraudulent activity was happening. In a decentralized system, you can't trust that the people who are creating these blocks aren't doing something fraudulent. So they could be manipulating these blocks in such a way to double spend, to increase their own Bitcoin stash. There's all sorts of things they could do to manipulate it. How do you prevent that sort of thing? And effectively, the proof of work is a sort of incentive system to not necessarily prevent fraudulent activity, but to make the opportunity costs of fraudulent activity really low. So the proof of work, sort of conceptually, it effectively incentivizes against the creation of forgeries by imposing a significant cost to produce a forgery and a low probability of success to any forgery. Now, it's not impossible to create forgeries, and this has happened increasingly in the past year or so, but the proof of work is a way to try and create a system that you can believe in without having to rely upon a centralized authority. So that's sort of the conceptual idea behind a proof. What is the proof then? So miners are racing to find a random string that will produce a proof that meets the right conditions. So the proof is effectively a hash value that is a function of three different elements. So it's a function of the current block hash, which is this thing right here. So the summary of all the transactions, the final hash value of the last, say, 10 minutes. It's that plus the hash value of the block before it, and then a random string, which then produces the proof hash. Now, what's known is the current block hash. That's a known element. The most recent block hash is a known element, but that random string is what's not known. So when we talk about Bitcoin mining, what's happening is all of these computers are trying to find that random string. Basically what happens is miners will try out every possible permutation of numbers and letters and strings to try and figure out what that random string is. And when they're successful, they'll know it. It'll meet the conditions of the proof hash. But this is what Bitcoin mining is all about, is constantly inputting random numbers until you finally find the right one. Does that make sense? I think that might be the most difficult part of blockchain. Yep.
So who the nodes are? So like the miners are the nodes, and they are doing this job kind of volunteer?
Yeah, good question. So they are volunteering, but this gets into a few slides from now. We'll talk about exactly why they do this. Because it is, it's a good question. Why would you spend all your time doing this? And also it takes a lot of computational power to do this. We'll go into later about how much computational power it takes, but it's extremely expensive to do this process. There's a question of why they do it. Basically it has to do with they get a lot of money from it. That's the short answer. Are there other questions at this point? Yep. So the conditions are built into the Bitcoin protocol, the piece of software that everybody is running. So it changes the conditions every single time, and then basically it randomizes that, and you have to have the software approve your random string. I should also mention, go ahead. Yes, we'll get into that in a short bit. So maybe I'll move on to the next stage here. And if anything is unclear, again, just let me know. So the proof difficulty, the difficulty of finding that random string, so it changes constantly. Now, Bitcoin, in the software, the Bitcoin protocol, aims to have a proof found once every 10 minutes. So that's part of the rules of the system. On average, every 10 minutes, that random string is found, a block is created, and it's added to the blockchain. Now what happens, though, is that we get more and more computers involved in the network, and it becomes easier to find that proof. It becomes easier to find that random string. So the system is also designed that as more computational power comes onto the network, the proof becomes more difficult to find. So the system actually adjusts the complexity of the proof problem to maintain this. And what we're seeing in the past year or two is companies like Bitmain creating chips which are designed solely for Bitcoin mining. So they become very, very efficient at solving that proof, at finding that random string. They can't do anything else. These chips are completely useless for anything else, but they're optimized to be to do the hash values for Bitcoin mining. But that means that there's more computational power come on, and it means it has to be more difficult to find that proof. This brings us to the chain. So each block is a hash of all of its transactions. So we saw here, the final hash value of the block summarizes all the transactions that have occurred in the previous time. But then when we go and create the actual block, we're also including the most recent block. But of course, that most recent block also includes the previous block before it. And this goes all the way back to the very origins of the blockchain, to what's known as the Genesis block. The Genesis block is also where that newspaper headline is stored. So this is why it's a chain. It's a chain of blocks. Every single one references every single transaction that's occurred from the beginning of the Bitcoin network. So that's why we talk about the blockchain. Now, once a proof is found, a valid block is then created. So you find a random string that meets the conditions, you produce a hash value which meets all the conditions. Now, just like that initial transaction, once that hash value is found, it's then shared across the Bitcoin network. And again, every computer on the network checks that that hash function, that transaction, meets the rules set out by the Bitcoin protocol. So every computer on the network is checking that this has met the rules. This is, in fact, a valid proof. If it meets the conditions, if it meets the rules, that block is then added to the chain. That's the core thing. So we've now started from a transaction, we've got to blocks, and we've now got a blockchain. Now, to answer an earlier question, why would you mine? The miner that finds the proof gets newly minted bitcoins as well. So every time a proof is found, bitcoins are created, and the miner that found it gets those bitcoins. Currently, you get 12.5 coins every time that you find the right random string, and that's worth about 62,000 pounds, last time I checked. Now, this happens every 10 minutes. So you can imagine how profitable it might be for somebody who has enough computational power to really successfully find the random string. You could potentially get 62,000 pounds every 10 minutes. So that's why people spend time, energy, all of this stuff on Bitcoin mining. I will say, so there's a sort of curious aspect about Bitcoin as well. It started off at a much higher reimbursement level to incentivize people to get onto the network. So it used to be, 25 coins. At a certain point in time, it got reduced to 12.5. Eventually, it's going to be reduced again, and eventually, there's going to be no more coins made. At that point, it raises a really big question. Why would you mine if you're not going to be getting these bitcoins anymore? And the answer is supposed to be that people who are doing these transactions are also providing a certain percentage fee every time they do a transaction. I don't think that's actually sufficient to maintain the Bitcoin network once it reaches its limits. But it's sort of a curious aside about how this thing is built. Okay, that's how Bitcoin works. Is that relatively clear? Are there any questions? Yep.
So basically, it's that I make a transaction, for example, to you,
Yep.
and the miner is in charge of validating if this contract works.
Yep.
So where the money come from for the miners?
So new Bitcoins are created, which is why it's called mining. But then also they might take a percentage of the transaction. So it might be 1%, 2% of every transaction, and they get all of that money as well. Yeah.
Of the actual coins themselves is just a byproduct of the hash function reaching the limit.
Yeah, so the value of the coins. Built into the system is the fact that they're scarce. And
The value, the number.
oh, yes, so 12.5 you mean?
No.
Nope.
Bitcoin is scarce because there's a certain number that will be produced.
Yep.
Once those are produced, that's it. So that finitude has to do with the hash function reaching its limit.
Not the hash function, but the Bitcoin protocol. which determines how many coins people get rewarded with, when it lowers, all these sorts of things, and eventually it lowers to nothing. So you can actually sort of forecast when exactly this is going to happen. I forget exactly when, but yeah, there's estimates of when it'll reach that point. So it's all built into the Bitcoin protocol, which is the rules of how this stuff works. Now, the beauty of this is that nobody oversees it. There is no single authority overseeing all of this stuff. It's a digital currency that has value, and people can't break the rules by double spending and doing that sort of stuff, despite nobody overseeing it. So it's a quite elegant solution to a lot of the problems that people were coming across when they tried to think about a decentralized digital currency. Okay. We're sort of running a bit short on time here, so I may speed through some of this, but I'll try and get across why blockchain is more important than just Bitcoin. So we might talk about blockchain 2.0, and in particular, we can talk about Ethereum. How many people have heard of Ethereum before? Okay, so a handful of people. So it's launched in 2015, and basically, the creator of Ethereum, Vitalik Buterin, who was a 19-year-old at the time, which always makes me massively envious that somebody at 19 is creating these things. He looked at Bitcoin's blockchain, and he realized that it was quite simple. And it was a bit too simple. It couldn't do a lot of things, and it didn't sort of fully explore the potential of this decentralized network of computers working together. So Ethereum consists of a blockchain. It has its own cryptocurrency called Ether, and then importantly, it also has a programming language associated with it. So not only can you sort of record transactions on Ethereum, you can also run programs on Ethereum. This network of computers isn't just about monitoring transactions, it can now be used to run various programs. So Buterin, for instance, oftentimes sort of says, well, Ethereum is like a global decentralized smartphone, which I think is a nice sort of way of thinking about it. Now, this programming aspect has allowed a whole series of new ideas to emerge. So we'll start off with one of the simplest ones, which are smart contracts. So smart contracts are simply tiny computer programs that transfer assets and money according to rules that have been agreed to by two parties. Now that sounds maybe a bit abstract, but let me give you a concrete example. Here is a very primitive smart contract, a vending machine. The implied contract is that if you put in X number of coins, you meet those appropriate conditions, in return you'll get a product, with nobody overseeing it. There's no centralized authority there overseeing it. It's a smart contract in the sense that once the conditions are met, then X happens, something else happens. So a vending machine is a good example of what a smart contract might be like. We can also think of something like a job contract. So the smart contract might lay out the conditions that have to be met for fulfilling that job. Once those conditions are met, then the contract automatically pays out money. Which, if you've ever done any freelance work and you've struggled to get somebody to pay you months later, it might be a rather nice feature if smart contracts just automatically paid you once the job was done. So that's one example of a smart contract. Another, and I find this quite dystopian actually, is a car lease. So this is one idea that's been imagined where the contract is you pay a monthly lease for access to your car, and the smart contract controls whether or not you get access to your car. If you don't make that monthly payment, you might get locked out. You can imagine this as well for smart homes. If you don't make a rental payment, you would get automatically locked out. I find all of that incredibly dystopian and worrisome, but the blockchain community seems to love these sorts of things. Now, the benefits of a smart contract, it makes it rather costly to breach a contract. So it's sort of just operating on the blockchain network, on the Ethereum network, and it becomes very difficult to sort of breach it. It can also incentivize decentralized groups of people to work together, even in the absence of any sort of manager overseeing all of it. So we can imagine a smart contract which was effectively for a group project. A group of people have to produce this project, and then once they produce it, they get paid. So that's a smart contract where nobody is overseeing the process, but it's coordinating and managing a decentralized group of people. So it's sort of an interesting idea about how it might be used. Now, slightly more sophisticated, people have started talking about decentralized applications, or dApps. And these are applications with their code stored on the blockchain. So they effectively use the network's processing power to run. So instead of the network's processing power being used just to mine things, it's now being used to run programs, to run applications. Now, the most fascinating part I find about these things is that they're not owned by anyone. So a really common example is something like a decentralized version of Facebook, which wouldn't be owned by Mark Zuckerberg, but could instead facilitate, decentralized peer-to-peer social connections, but without Zuckerberg just making a ton of money off of our personal data. So it's an interesting idea. Maybe we can move away from centralized platforms owned by particular people to decentralized platforms operating on a blockchain network. So why dApps? First of all, no downtime. Most applications, internet-based applications, are stored on one server. If that server goes down, that means that there's downtime for access to it. With a decentralized network, it becomes much more difficult for that whole thing to go down. So as long as there's computers connected to the network, it'll still be running. You can also avoid intermediaries. So again, this is the idea that we could cut Mark Zuckerberg and Facebook out of the loop, that we could just connect individually, peer-to-peer. So we don't need intermediaries. Hacking can be more difficult on a decentralized application. Data, for instance, is stored in encrypted formats, so it becomes much more difficult to steal personal data. And then it's also open source. So everybody can view the blockchain, because blockchains are public. You can go and look at the code. You can see exactly what the code is doing. Is it spying on you? Things like that. One example, which maybe some of us have come across already, this isn't quite a decentralized application, but it somewhat gets to the idea, which is BitTorrent. So if you're downloading films off the internet or sometimes music, you've probably used a torrent program before, and this is a peer-to-peer decentralized file sharing program. So you download the file from multiple people connected on the network rather than downloading it from one single server. Another example might be a blockchain-based Airbnb. So again, why do we need Airbnb in the middle? We could put that application onto the blockchain, not owned by anyone, and it could be designed to perform all the same functions as Airbnb, but without that intermediary taking a cut of every single thing. So transactions would be conducted peer-to-peer. You'd have messaging functions, you'd have search functions, you'd have everything that we have with Airbnb, but without money going towards a centralized platform. That's the promise of decentralized applications, at least. I'll very quickly go through some of the uses already for blockchain. Supply chains. Blockchain is starting to be used in supply chains. Again, if we think about it as a spreadsheet which monitors transactions, that's what you sort of need in the supply chain. You need to know where, for instance, has food come from. And a blockchain might be a nice, simple way to monitor where food has come from. Is it contaminated? How old is it? All this sort of stuff. So IBM right now is working on a version of this, so IBM Food Trust, and it aims to put the food supply chain onto a blockchain. Another example, ethical supply chains. So organic food or fair trade food or products that haven't involved child slavery how do we know that the products we're buying don't actually include child slavery? Well, blockchain might be one way to track the sort of the movement of a good from its origins to us buying it in the store. So again, this is a way to sort of monitor all of this stuff. One example that's already in use is cobalt tracking. So all of our smartphones have cobalt in them. It's absolutely essential to a lot of digital technology today. The problem is a lot of cobalt involves child labor, it involves horrible working conditions, it involves basically sort of armed gangs forcing people to do the work for them. So if we want ethical sources of cobalt, blockchain might be a way to track the source of it all. I won't get into that. Lastly, let's get into some of the problems, which I think is really important. So I've talked about a lot of the benefits of the blockchain. Now let's talk about some of the major problems. First question, is it efficient? So it can be very slow to process transactions. The proof of work, finding that random string, takes time. So your transaction is not verified for quite a bit of time. When I send people money digitally through my NatWest app, that money automatically goes through. On the Bitcoin network, it takes a lot longer to do that sort of thing. Another problem is there's not many transactions possible at any one given time. So Bitcoin, the network can handle up to 7 transactions per second. By contrast, Visa's payment system handles about 56,000 transactions per second. And this is sort of a fundamental limit built into the Bitcoin network. So it's not something which can be easily changed. Crucially, the energy question, which hovers around, rightfully so, every discussion of Bitcoin and blockchain. So the proof of work protocol is explicitly set up to waste energy. So the people who are running these processes to find that random string, they're wasting energy. They have to pay for electricity in order to run their computers again and again and again. So that's built into the system. The proof of work requires spending energy and electricity. This, I thought, was a nice Twitter summary of what exactly Bitcoin mining is all about. So periodic reminder that Bitcoin mining is not solving equations. It's thousands of GPUs and specially built chips burning electricity to yell random 64-digit numbers at each other in the hope that one of them is the secret word of the day. Which is just a perfect description of what exactly is going on in the Bitcoin network. It's nothing fancy. It is literally computers shouting at each other to find the random word of the day. Now, this is, I think, the most astonishing part. How often does this happen? Well, you can see here from the chart, and you can go and check out this, the updated version on the website. Currently, the Bitcoin network as a whole creates, what is that, 52, I think it's 52 quadrillion hashes every single second. So that hash function that we started the day with, that is happening every single second, 52 quadrillion times, and you can see that it's exponentially increasing. The simple reason why is because companies like Bitmain are producing these chips which are much more efficient at doing it, so it's happening much, much quicker and much, much more as a result. So that's an insane amount of, and remember, the hash is just shouting a random number at other computers. There's nothing significant or important going on here. It's literally just a way to waste energy to incentivize against fraudulence. This all transmits into a huge amount of energy use. Now, there's a number of different estimates about how much energy the Bitcoin network currently uses. The lower estimate is 2.6 gigawatts, which is about comparable to how much energy Ireland uses. And the upper is 7.7 gigawatts of energy, which is about how much energy Austria uses. So the entire Bitcoin network is using as much electricity as entire countries. Now, we set that in the context of, here's the sort of curious thing. Bitcoin mining, because you're doing so much computational stuff, it generates a lot of heat. And what we're seeing is that Bitcoin miners are now moving to the coldest spots in the world simply because you then don't have to pay to cool down your computers. So the Arctic is becoming one of the key places to place Bitcoin mining. Iceland and Greenland and Upper Canada, all of these places are now becoming very popular for mining. Also in caves is another place, sort of getting away from the sun and all of that. All of that Bitcoin mining, all of that energy being used just to shout random numbers, you set that then in context of climate change. So here is 1960 temperatures versus 2017, and we can see that everywhere temperatures are increasing. Everywhere we're seeing more and more extreme weather events, and the predictions are, our best knowledge says that this is only going to get worse and worse and worse. So right now, we should be cutting back on energy use, but instead we've got all these computers shouting 52 quadrillion random numbers at each other every second for some reason. So I think that's a really big question that hangs over the Bitcoin ideology, the Bitcoin network. Is it a good use of energy? Should we be doing this sort of stuff? Now, I should mention that there are some proposed solutions. New hardware tends to be much more energy efficient. The problem is that as the stuff gets more energy efficient, people just use more of it. So more energy efficient hardware isn't really a solution. A better solution is moving away from proof of work to alternatives. So things like proof of stake, proof of elapsed time, proof of useful work. There's alternative ways to perform that same function without having to use all these computers shouting numbers at each other. The problem for the Bitcoin network is that when you move away from the proof of work, you start having to rely upon third parties again. So all of these alternatives pose real challenges for the sort of ideology around Bitcoin. They rely upon third parties. They rely upon trusting other people. So a lot of people are very hesitant to move away from the proof of work despite the energy problem. I'll leave it at that for today. If you have any questions, we can discuss them in the seminars. I know that's quite a bit to take in. Next week, we'll be talking about AI in the economy. So automation and monopolization.
No hay consistencia en cómo avanzamos todo esto, ¿no? ¿Cómo? Digo que hay una consistencia en cómo se... No, es como...